All right, time for some similarity practice here. So we have a triangle A prime, B prime, C prime. That's a dilation of ABC. We're told that in the problem here. And we want to find the center of dilation. So to find the center of dilation, we're going to draw a line, with the ruler would be best, from C prime through C, from A prime through A, and through B prime through B. And notice they all pass through the point M. All right, so M is the center of dilation because these projection lines A prime, B prime, and C prime all pass through point M. Or we could say they intersect at M. All right, so we're told here that A prime, B prime, A prime, C prime, that's the distance between AC. So that's this length right here. So this length right here is 3 times the length of AC. So whatever this is, it's 3 times that. That's what this means, that ratio. MA prime, that's from here to here. So this distance right here is 3 times bigger than the distance from M to A. That's what this is telling us here. All right. So that's 3. So the top thing is 3 times bigger. That's why that ratio is 3. So the question here is to name 4 additional ratios that equal 3. Now remember, a ratio is a fraction. So let's find some more. So we got some more sides. How about B prime, C prime? That's this big side over here. That's 3 times bigger than BC. And then we have this other side, A prime, B prime. We haven't mentioned that yet. A prime, B prime. That's 3 times bigger than AB. And then we have the distance from, we said M to A prime. Well, what about M to C prime? This whole distance right there. From M to C prime, that distance is 3 times bigger than M to C. And then M to B prime is 3 times bigger than MB. So these are all, we could put equals in between all these because they're all equal to 3. Okay, because if the scale factor is 3, then the sides are 3 times bigger, and the distance of these points is 3 times farther than the distance to the original points. So those are ratios there. There's 4 different ratios. Okay, now again, we're told the same thing. A prime to C prime is 3 times bigger than AC is 3. And we're also told that a double prime, C double prime, so this length right here is half of this length right here. A double prime, C double prime compared to AC is 1/2. In other words, AC is twice as big as A prime double prime. That's what this is telling us. So if we compare these here, now we're looking at A double prime, B double prime. Okay, so the numbers don't matter because it's the ratios, and we don't really know the lengths. I mean, I guess you can measure them with a ruler, but, you know, let's say this was 1, all right, and we want to compare that to this length. Okay, well, this doubled makes this AB because this is half. Let me do it in a different color. That's 1, so this would be 2, and then we know that the scale factor from this to this is 3 times larger. Right, so this is going to be 6. Again, we're playing a what-if game here. All right, so if that was true, then this would be a 1 to 6. All right, that one's actually 6 times larger, so 1/6. Notice we got small over big here. All right, so basically it doubles and then triples, so that's where the 6 is coming from, right? What about the ratio of B prime, C prime? That's over here. To B double prime, C double prime. Well, it's going the other way around now. Okay, so we're starting with this. This is going to be 1/3 of that. This is going to be 1/2 of 1/3, which is 1/6. Actually, it's going to be the other way around. So 6, because the largest number is on top, 6 over 1, which is 6. All right. So that's the idea. You know, another little side note, we could call this 1x, 2x, and 6x. That would also kind of do the same thing there, because we don't exactly know what it is, but we know that this one is 6 times bigger than the small one. Okay, Now we want to write some proportionality statements, all right? So remember, a proportion is written as A over B equals C over D. That is a proportion, one fraction equal to another fraction. And so we want to write some true proportionality statements here, and there's lots that you can do here, okay? So we can do some comparing, small triangle to large triangle, okay? We could go small to large, okay? So let me do a small triangle over large triangle. So that would be something like A prime C prime over AC. Okay, so that's taking a side from this triangle to this triangle. Now, for my other fraction, I got to take another side from this triangle over that one. Okay, so that would be B prime C prime over BC. That would work. Okay. We could also take and write a proportion. We can put two sides from the same triangle, small, large. All right. And so I could take two sides from the small triangle, like AC and CB. Let's compare those. AC over CB. Now I got to take the corresponding sides. That would be A prime C prime over C prime B prime. Okay, that will also be true because we have corresponding parts horizontally and vertical. These two correspond because these are the top sides, these are right sides. These correspond because they're both in the small. These are related because they're both in the large, so on and so forth. All right. So that's the idea there. And then we're asked to use the center of dilation for one of them. All right, so let's use this M point. So we could say MC prime, that's the distance from M up here to C prime. So that's, maybe we'll put that over MC. And that ratio, which we already said before was 3, is going to be the distance from MA prime to MA. All right, we kind of already said that one there. Okay, we could also do proportions down to here. We could say, however, the center of dilation actually for these two is N. So if you're going to use this center of dilation, you have to use NA and NA double prime, NC and NC double prime. All right. So lots of ways to make proportions, but again, these are proportions. One fraction equal to another fraction. That's a proportion itself. That's a proportion itself. That's a proportion. All right. So again, we know these ratios for 3 1/2. So let's talk area. So the area, if the area of A double prime C B A double prime B double prime C double prime is 6 units, all right, that's the small one. Find the area of the two other triangles, all right? So let's talk area. Well, what happens to the area as the triangle grows? So the key is that the area is not equal to the scale factor. Remember that? We saw that the area is the scale factor squared times bigger, okay? So if we take this little triangle right here, this A, B, C, A prime, B prime, C prime, if we were to copy that up to here, which this one was doubled, all right, we're going to see, let's see if I can draw this well. If we take that one up there, and there it is. All right, so not a perfect drawing, but we're going to actually be able to fit, this is, the sides are doubled, but the area is 4 times bigger. We could fit 4 of those triangles in here. 1, 2, 3, and this upside down 1, 4. I just freehanded it, so it's not perfect, all right? So the key again here is that the new area is the scale factor squared times the old area. All right, so if we take one figure and we multiply it by the scale factor squared, we get the new area. All right? So we know that ABC is twice as big. So this ABC is twice as big in length, right? So we said if this side here was 1x, then we said this side here was 2x, twice as big. And this side over here would be 3 times as big as that one. So that'd be like 6x because it's 3 times that. So anyways, so this is twice as big. So if the sides get twice as big, the scale factor is twice as big. So we're going to have 2 squared, which is 4, times the original area, which is 6. So that's 4 times 6, which is 24 square units. All right. Now, going from the small triangle, the double prime triangle, because again, we're told the double prime triangle here. So going from the double prime to the single prime, how many times bigger is the double prime to the single prime? Here the scale factor was 2. Going from double prime to the original is twice as big. Going to the largest triangle, that's 6 times as big, we've already talked about. So from here to here, it's doubled and then tripled. So this big one here is 6 times bigger than this. That means that I could fit 36. I'm obviously not going to be able to draw them all, but I could fit 36 of these in here. I could fit a whole bunch, all right? Something like this. And I could stack a whole bunch in there. I could fit 36 of them in there. All right, so here the scale factor going from is K equals 6, going from A double prime, B double prime, C double prime, triangle, to triangle A prime, B prime, C prime. So we're going to take 6 squared, taking that scale factor squared, times the original area, 6. And this is the area of A double prime, B double prime, C double prime. All right, so that's 36 times 6, and that's 216 square units. All right. So lots of things we can do with those similar triangles. And let's go ahead and look at the next page here. So we've seen that we have 2 ways to show that polygons are similar. One way to show that they're similar is if polygon or figure is a dilation of the other. All right, so if one is a dilation of the other, then we know that they are similar. And we just have to show that they have a center of dilation for that. The other method we learned is to figure out if 2 things are true. And we can check to see if corresponding angles are congruent and the corresponding sides are proportional. And we have to check all of them to see if they're similar. However, for triangles, we have some shortcuts to remember. So triangle similarity shortcuts or theorems. We have 3 of them. We have the angle-angle similarity. If 2 angles are congruent, then they are similar. We have side-side-side similarity. And we have side-angle-side. And we want to see here in these ones, in these problems here, if they are similar by one of these 3. So here we have some 2 triangles, and we look at their angles. Are their angles the same? Well, it looks like no, but we got to be careful. We got to find that 3rd angle there, right? So let's find that there. Let's say 79 plus 60 plus x equals 180. And so this is 139. And if we subtract 139 from both sides, then we get 41. So this is 41 degrees. And so, yes, indeed, we have 79 degrees and 79 degrees. we have 41 degrees and 41. So these are similar by angle-angle theorem. Okay, now we need to write a similarity statement. So let's get that in there. So our similarity statement here, since they are similar, would be triangle ABC is similar. Let's get the order right. A corresponds to D. Those would both be the 60s. B is 41. That corresponds to E. And we're left with F. All right. And our reason is angle-angle. What about this one here? Are these two similar? Well, we have a couple congruent angles, and so maybe this is side angle side. All right, so let's go ahead and check the ratio of sides. So 16 and 20 correspond. Actually, let's do this. A better way to do this is to take the 16 and this 20. Okay, because those two make this angle. And take the two that make the M angle. That's 20 and 26. Now watch out. Don't flip-flop these. Make sure. If I put small over large, I got to put small over large. Okay? And actually, let's do a little color thing here. Okay, let's check that 20 and that 26. All right, so we want to compare those two, see if they're the same. We can do this a couple ways. We can simplify the fractions to see if we get the same thing, or we could cross multiply, or we could divide them out in our calculator, 16 divided by 20, and get a decimal. Probably the easiest way without getting your calculator out is just to simplify the fraction. 4 goes into 16 4 times, so divide this by 4 and divide this by 4, we get 4/5. Divide this by 2. It looks like 2 is a common factor there. We get 10. Divide 26 by 2 as we get 13. Are those the same? No way. So we simplify the fractions. You've got to simplify it to actually say, nope, can't simplify those any further, and they're not the same. So these are not similar because the sides are not proportional. It almost looks like side angle side, or you could even check side, side, side. So the key word there is not proportional. Okay? And so one more. Are these similar? Well, they got angles. Now right away it looks like the angles may not be, but we got to find the missing angle. Let's call this y since it is y there. We've got 77 plus 48 plus y has to be 180. So if we add these up, we get 125. Subtract 125 from both sides. And y is 55. So this is 55. Do those angles agree? No. There's no 66 in this. So there's a 48. Yep. Those correspond, but these do not. So the corresponding angles are not congruent, so these are not similar. Not similar. Got to give a reason. Because the corresponding angles are not congruent. Okay. All right, so that's the idea. So those are using our 3 triangle shortcuts there. Now we're going to use the side splitter theorem here. The side splitter theorem tells us that when we have a triangle, and if we have a line that is parallel to one of the sides, and let's say these little pieces are A, B, C, D, then we know that A over B equals C over D, and that is the side splitter theorem. All right. A over B equals C over D. All right, so we want to look for AG here. So we got all these little pieces here. Looking for AG. Well, AG corresponds to AB. So let's use this little triangle there, all right? We got the 6 piece we know. We've got AG that we don't. We got the 10 and we got the 4. So we can say 6 over AG equals 10 over 4. And we can cross multiply that. 6 times 4 is 24 equals 10 times AG. Divide both sides by 10. And we get AG, if we simplify that fraction, we get AG is 12 fifths. If you want to go plug that in and get a decimal, you get 2.4, but that fraction is just fine. All right, FC. How about this one? Now this one we can't use the side splitter on here because this is not one of the sides that is being split. Okay, it doesn't apply here, so be careful. So FC, let's go ahead and get a proportion there. We've got FC. What does FC correspond with? Well, FC corresponds to this 2 here. All right, so FC is that kind of horizontal side, somewhat horizontal. And so is 2. Now let's look at this triangle right here. Let's focus on that triangle and the little triangle that's inside of it. So there's 2 similar triangles there. FC is in the big triangle, 2 is in the little triangle. What's the side of the big triangle there? It's 14. So we've got to take the big side over the little side, which the little side is 4. Now we got the 14 because we added them. Don't forget to add these. 10 is just that part, 4 is that part. You got to add them. And we get that. All right. Now we can cross multiply and solve. So we get 4 times FC equals 2 times 14, which is 28. And now let's divide both sides by 4. And we find out that FC is 7. All right. Great. Not a lot of room here. How about FE? So we got this was 7. We'll go ahead and label that there. All right, moving on to FE. This is a nice one. We can use side splitter again here. FE. Notice it corresponds to this 8 over here. We also have this 6 and this 10. So let's take a fraction. Again, the side splitter works really nice because this missing side over this equals this missing, that side that we know over that side that we know. See the proportion? So it lays out really nicely. The side splitter theorem does. So that's what we'll use there. All right. So let's go with FE over 6 equals 8 over 10. You can put those in different orders if you like, but we get 10 times FE and 6 times 8, which is 48. Divide both sides by 10. We get 48 over 10. And we just simplify that fraction. 2 goes into both those, 24 fifths. Again, if you want to make that into a decimal or a mixed number, you can. It's going to be what, 4.8? Because 5 times 5 is 25, so it's going to be 4.8. But that's just fine to leave it that way. Moving on, ED. So we got 24 fifths there. Got that one, ED. All right, that's another horizontal one there. So we're going to compare it kind of like we just did with FC. Okay, so let's go with ED, ed, over. Now you could use a 7, but you might want to use this one that we know just in case, you know, oops, we made a mistake on that 7. If you can avoid reusing numbers, that's nice when you're doing a problem like this because you might have made a mistake. So ED, let's do it over 2. Let's compare the big triangle to this little triangle. That horizontal over that horizontal. And that would be this whole side, which we've got to add these up. 10 plus 8 plus 4 is 22 over 4. Now, there's other proportions you can use for this, but let's go with this. 4 times ED equals 2 times 22. We're cross-multiplying here. That's 44. And then let's solve that by dividing by 4, and we got a nice, neat 11. So that guy is 11. What else do we have here? All right, we got AE. That's this whole side. Now, we could add these up. That'd be fine. This one was 12/5. All right, we could add those up and get this. AE is 12/5 plus 24/5 plus 6. All right. If you want to go decimal, you can, and that would be fine. All right. But hey, good chance to practice some fractions. We've got to get better at our fractions. That 6 is 30/5. All right. So I'm going to go ahead and practice some fractions. 6 is like 6 over 1, which is 30/5. And if we add all those up, they're all fifths now. So we have 12 and 24. That's 36 and 30. That would be 66/5. Or that's going to be in decimal, what's 13.2. All right. There you go. And last but not least, AD, just add them all up. AD is 4, add up all the sides, 4, 10, and 8. And that would be 22. That's for AD. All right, so AD is going to be 22. Let's just, for sake of room, let me just clean that up. All right, found all those pieces there. Lots going on in a little space. All right, last one. We got a proof here. So we want to prove that these triangles are similar, all right? And so we know the lines are parallel, okay? So that's the first thing there, all right? AB is parallel to DC, and that's given. All right, now you can do a couple ways, couple kind of proofs here. You could do a paragraph proof. You could write this kind of out in words, or you could do a 2-column proof if you'd like, which just kind of save some words, save some ink or graphite with your pencil. All right, I'm going to do a little 2-column. All right, if you want to just kind of write this out in words, it's totally fine. All right, again, we got AB is parallel to CD. We got to point that out, and that's given to us because it's drawn in the statement or the picture. And that means we got some alternate interior angles. So these guys have to be congruent. So angle A is congruent to angle C. And these ones have to be congruent, B and D. Angle B is congruent to angle D. And we'll give the same reason for that because these are alternate interior angles. And the alternate interior angle theorem says that if the lines are parallel, then the alternate interior angles are congruent.